Your brain is executing thoughts that aren't yours. Right now, as you read these words, your consciousness is experiencing a narrative that feels entirely self-generated, entirely yours. But what if I told you that the very act of thinking, the sensation of deliberation, choice, and intellectual control, is itself a computational process running on biological hardware that you don't consciously direct? What if the thoughts you believe you're generating are actually being executed by systems far deeper than your awareness can reach? This is not philosophy. This is mathematics. This is Alan Turing's most unsettling discovery, and it fundamentally rewires how you understand your own mind. We live in an age obsessed with the illusion of conscious control. We believe we think our thoughts. We believe we make our decisions. We believe that somewhere inside our skulls, a unified self is steering the ship of consciousness, weighing options, deliberating carefully, and arriving at conclusions through some mysterious process we call free will or reasoning. But this belief is so deeply embedded in our culture, so reinforced by every story we tell ourselves, that we've stopped questioning it entirely. We assume that thinking is something we do, not something that happens to us. We assume that the mind is transparent to itself, that consciousness has direct access to its own mechanisms. And we assume that intelligence, whether human or artificial, must involve some form of intentional, deliberate processing that we can introspect and understand. Every single one of these assumptions is wrong, and the man who proved it was Alan Turing, a British mathematician who spent his life asking the most dangerous question in the history of thought. What if thinking is just computation? What if the mind is a machine? What if you are not the author of your thoughts, but merely the audience watching them execute? The story begins not with Turing, but with a crisis. In the 1930s, mathematics itself was collapsing. For centuries, mathematicians had believed that all true statements could be proven, that logic was complete, that the universe of mathematics was a closed system where every question had an answer. Then Kurt Gödel shattered this dream. In 1931, he proved something that should have been impossible. There exist true mathematical statements that cannot be proven within any consistent formal system. The implications were devastating. If mathematics, the most rigorous, most certain form of human knowledge, was incomplete, then what hope was there for certainty anywhere else? The foundations of logic itself were crumbling. But there was another crisis lurking beneath this one, and it was even more fundamental. David Hilbert, one of the greatest mathematicians of the era, had posed what seemed like a simple question in 1928, the Entscheidungsproblem, or the decision problem. Given any mathematical statement, is there a mechanical procedure, an algorithm, a step-by-step process that can determine whether that statement is true or false? Hilbert believed the answer was yes. He believed that all of mathematics could be mechanized, that thinking itself could be reduced to a procedure. He was asking, in essence, can we build a machine that thinks? Can we automate reasoning itself? This question haunted the mathematical world. If the answer was yes, then mathematics could be fully mechanized. If the answer was no, then there were limits to what could be computed, limits to what could be known through pure logic. The answer would determine the future of mathematics, the future of logic, and ultimately the future of our understanding of the mind itself. And the man who answered it was a young, brilliant, socially awkward mathematician named Alan Matheson Turing. In 1936, at the age of 24, Turing published a paper that would change everything. The paper was titled On Computable Numbers, with an application to the Entscheidungsproblem. In it, he did something extraordinary. He didn't just answer Hilbert's question. He invented an entirely new way of thinking about computation, about machines, about the nature of thinking itself. He created what we now call the Turing machine, not a physical device, but a mathematical abstraction so powerful that it would become the foundation for all modern computing. The Turing machine was deceptively simple. Imagine an infinitely long tape divided into squares. Each square contains a symbol, either a 0, a 1, or a blank. There is a read-write head that can move left or right along the tape, reading the symbol in the current square, writing a new symbol if needed, and moving to an adjacent square. The machine operates according to a fixed set of rules. If the current symbol is 0 and the machine is in state A, then write a 1, move right, and go to state B. If the current symbol is 1 and the machine is in state B, then write a 0, move left, and go to state A, and so on. The rules are deterministic, mechanical, and completely devoid of any intelligence or understanding. The machine doesn't know what it's doing. It doesn't understand mathematics. It doesn't have intentions or goals. It simply follows its rules, step by step, mechanically, without consciousness or comprehension. And yet, and this is the crucial insight, any computation that can be done by any machine, any algorithm that can be executed by any device, can be done by a Turing machine. This is the Church-Turing thesis, and it is one of the most profound statements in the history of science. But here's where it gets dangerous. If any computation can be done by a Turing machine, and if a Turing machine is just a mechanical process following simple rules, then any computation can be reduced to mechanical rule following. And if thinking is computation, if reasoning, deliberation, and consciousness are all computational processes, then thinking is just mechanical rule following. Your thoughts are not being generated by some mysterious inner self. They are being executed by your brain, which is itself a biological machine, following rules that you don't consciously understand and cannot consciously control. You are not the author of your thoughts. You are the stage upon which they perform. This realization should terrify you. But it gets worse. Turing proved something else in that same paper, something that would haunt mathematics and computer science for the rest of the 20th century. He proved that there are problems that no Turing machine can solve. There are questions that no algorithm can answer. There are limits to what can be computed, and therefore limits to what can be known through pure logic and mechanical procedure. The most famous of these is the halting problem. Given any program and any input, can you determine whether that program will eventually halt and produce an output, or whether it will run forever? Turing proved that no algorithm can solve this problem. There is no mechanical procedure that can answer this question for all possible programs. The halting problem is undecidable. It cannot be computed. Think about what this means. There are questions that are perfectly well-defined, perfectly meaningful, but that no machine, no matter how powerful, no matter how sophisticated, can answer. And if thinking is computation, if reasoning is mechanical rule-following, then there are questions that no mind can answer either. There are limits to what human intelligence can know. There are truths that exist but cannot be proven. There are problems that cannot be solved. The universe of thought has boundaries, and those boundaries are absolute. Turing had answered Hilbert's question. The answer was no. Not all mathematical problems can be mechanized. Not all questions can be answered by an algorithm. There are limits to computation, and therefore limits to thought. But in answering that question, Turing had done something far more radical. He had created a mathematical model of what a machine is, what computation is, what thinking could be. And he had proven that this model had fundamental limitations. He had shown that the mind, if it is a machine with boundaries. And he had done all of this without ever building a physical computer. He had done it with pure mathematics, pure logic, pure thought. The implications were staggering, but they were also abstract, theoretical, removed from the practical world. Then came World War II, and suddenly Turing's theoretical insights became desperately, urgently practical. The Nazis had developed the Enigma machine, a device that could encrypt messages using a rotor system of such complexity that it seemed unbreakable. Every day, German U-boats transmitted encrypted orders. Every day, the Allies tried to intercept and decode these messages, and every day, thousands of soldiers died because the Allies couldn't understand what the Germans were planning. The Enigma machine used a system of rotating disks, each with 26 letters. The operator would type a message, and the rotors would scramble it according to a daily key. The number of possible configurations was astronomical. With 3 rotors, there were 26, 17, 576 possible starting positions. But the Enigma machine used more than 3 rotors, and the daily key changed constantly. The total number of possible configurations was in the billions. To break the code by brute force, by trying every possible key, would take years. The Germans believed the Enigma was unbreakable. They were wrong, and the man who broke it was Alan Turing. Turing understood something that the Germans didn't. He understood that the Enigma machine was itself a computational device, and that any computational device could be analyzed, modeled, and ultimately defeated by another computational device. He designed a machine called the bomb, named after an earlier Polish device, that could systematically test thousands of possible Enigma configurations per second. The bomb didn't use brute force. It used logic. It used the mathematical properties of the Enigma machine itself to eliminate impossible configurations, to narrow down the search space, to find the daily key in hours instead of years. The bomb was not a computer in the modern sense. It was an electromechanical device, a machine made of gears and relays and rotating drums, but it was a machine that could think, in a sense. It could solve problems. It could execute algorithms. It could do what only human mathematicians had been able to do before: break codes, find patterns, discover hidden information. And it worked. The bomb, operating at Bletchley Park, broke the Enigma code. Historians estimate that this single achievement shortened World War II by several years and saved millions of lives. A machine had done what human minds alone could not do. A machine had thought its way to victory. But Turing understood the deeper significance of what he had accomplished. He had built a machine that could solve a specific problem, breaking the Enigma code. But the principles behind that machine were universal. The same logic that could break codes could solve other problems. The same computational principles could be applied to mathematics, to logic, to any domain where information could be processed, and patterns could be discovered. Turing began to imagine a machine that could be programmed to solve any computable problem. A universal machine, a machine that could execute any algorithm, solve any problem that was theoretically solvable. This was the concept of the universal Turing machine, and it was the blueprint for the modern computer. After the war, Turing worked on the design of early electronic computers. He contributed to the ACE, the Automatic Computing Engine, one of the first stored program computers. He wrote papers on machine intelligence, on the possibility of artificial intelligence, on what it would mean for a machine to think. And in 1950, he published a paper that would become one of the most influential and controversial papers in the history of science: Computing Machinery and Intelligence. In this paper, Turing asked a question that seemed almost absurd at the time: can machines think? His answer was characteristically pragmatic and devastating. Instead of trying to define what thinking means, a philosophical quagmire that had consumed centuries of debate, Turing proposed a test. Imagine a human interrogator in a room, communicating via text with 2 entities, a human and a machine. The interrogator cannot see either entity. The interrogator can ask any questions they want. If the interrogator cannot reliably distinguish the machine from the human based on the responses, then the machine is thinking. It is intelligent. It has passed the Turing test. This test was revolutionary because it shifted the question from the metaphysical to the practical. It didn't matter whether the machine was really thinking in some deep philosophical sense. It didn't matter whether the machine had consciousness or understanding or intentionality. What mattered was behavior. What mattered was whether the machine could produce responses indistinguishable from human responses. If it could, then for all practical purposes, it was thinking. And this insight that thinking could be defined behaviorally, that intelligence could be measured by output rather than by internal mechanism, would become the foundation for artificial intelligence research for decades to come. But the Turing test revealed something even more unsettling. It revealed that we have no reliable way to know whether anything is truly thinking. We cannot access the internal mechanisms of another mind. We can only observe behavior. We can only infer consciousness from external signs, and if a machine could produce behavior indistinguishable from human behavior, then we would have no grounds for denying that it was thinking. We would have no way to prove that it wasn't conscious. The boundary between thinking and not thinking, between intelligence and mere computation, became blurred. It became uncertain. It became perhaps meaningless. Turing had taken the question, "Can machines think?" and transformed it into something far more disturbing. How would you know if they could? And by extension, how do you know that you're thinking rather than just executing a program? This is the core of Turing's insight. This is what makes his work so dangerous. He showed that thinking, whatever it is, can be mechanized. It can be reduced to computation. It can be executed by a machine following simple rules. And if your brain is a machine, and neuroscience increasingly suggests that it is, then your thoughts are being executed by that machine. You are not generating your thoughts. Your brain is generating them. You are experiencing them. You are the audience, not the author. Consider what happens when you solve a mathematical problem. You sit down with a piece of paper. You write down the problem. You think about it. You try different approaches. You make mistakes. You backtrack. You eventually arrive at an answer. You feel like you solved the problem. You feel like you did the thinking. But what actually happened? Your brain executed a series of computational steps. It retrieved relevant information from memory. It manipulated symbols according to learned rules. It compared results against known patterns. It generated new hypotheses and tested them against the constraints of the problem. Every step of this process is computational. Every step follows rules. Every step is mechanical in the sense that it is determined by the state of your neural network and the input you're processing. You didn't consciously direct any of these steps. You didn't choose which neurons to fire or which synapses to strengthen. Your brain did that automatically, unconsciously, mechanically. And yet the result feels like conscious thought. It feels like you solved the problem. It feels like you did the thinking. But you didn't. Your brain did. You just experienced the output. This is true for all thinking. When you have a conversation, your brain is executing language processing algorithms that you don't understand and cannot consciously control. When you make a decision, your brain is running decision-making algorithms that operate largely outside your awareness. When you have a creative insight, your brain is recombining patterns in ways that feel spontaneous and original, but are actually determined by the structure of your neural network and the information it has been exposed to. You are not the author of your thoughts. You are the stage upon which they perform. You are the audience watching a play written by your own brain, a play whose script you cannot read and whose author you cannot interview. This realization has profound implications. If your thoughts are being executed by your brain, and if your brain is a physical system subject to the laws of physics, then your thoughts are determined by physical law. They are not free, they are not chosen, they are computed. They are the inevitable output of a deterministic system given certain inputs and initial conditions. This is the problem of free will, and it is not a new problem. Philosophers have grappled with it for centuries, But Turing's insight gives it a new form. It's not just that your actions might be determined by prior causes, it's that your thoughts themselves are computations. They are mechanical processes. They are algorithms executing on biological hardware. But here's where Turing's work becomes even more radical. He proved that not all computations can be completed. He proved that some problems are undecidable. He proved that there are limits to what can be computed. And if thinking is computation, then there are limits to what can be thought. There are problems that your mind cannot solve, not because you're not smart enough, but because no mind could solve them. There are questions that cannot be answered through pure reasoning, no matter how brilliant you are. There are truths that exist, but cannot be proven. There are limits to human knowledge that are not limitations of human intelligence, but limitations of computation itself. This is perhaps Turing's most profound insight. It's not just that your thoughts are mechanical, it's that mechanical thinking has absolute boundaries. There are things that cannot be computed. There are questions that cannot be answered. There are problems that cannot be solved. And these limitations are not accidental. They are fundamental. They are written into the very nature of computation itself. Consider the implications for artificial intelligence. We are building machines that can process information, recognize patterns, generate text, make decisions. We are creating systems that can pass the Turing test, that can produce behavior indistinguishable from human behavior. But according to Turing's own theorems, these machines will have the same limitations that human minds have. They will be unable to solve undecidable problems. They will be unable to answer unanswerable questions. They will have boundaries to their knowledge and capabilities that are absolute and unchangeable. This means that artificial intelligence, no matter how advanced, will never be omniscient. It will never be able to solve all problems. It will never transcend the fundamental limitations of computation, and neither will you. Your mind is a computational system. It has the same limitations. You cannot solve undecidable problems. You cannot answer unanswerable questions. You cannot know everything. There are absolute limits to what you can understand, and those limits are not due to your individual limitations, but to the limitations of computation itself. This is the hidden message in Turing's work. This is what he discovered and what he tried to communicate to the world. Thinking is computation. Computation has limits. Therefore, thinking has limits. And those limits are absolute. They cannot be overcome by intelligence, by education, by effort, or by technology. They are written into the fabric of reality itself. You are not the author of your thoughts. Your brain is executing them. And your brain, like all computational systems, has boundaries that cannot be crossed. You are a machine. Your thoughts are algorithms. Your consciousness is the output of a deterministic process. And there are things you will never be able to know, problems you will never be able to solve, questions you will never be able to answer. This is not pessimism. This is mathematics. This is Turing's final warning. And it is the most important truth about the human mind that we have ever discovered.